Hey guys, all right, we are on slide 42, so restoring forces and Hooke's law. So I started this video yesterday and then I got into a coughing attack. I swear I don't have the coronavirus, but anyway, I had to stop for the night. So, all right, we've talked about potential energy as far as gravitational potential energy, but this is sort of the idea of potential energy whenever there is like a rubber band or a spring, something like that that's involved. And you know that if you take a rubber band and you pull it back, well, if you flip it or you let go, what does the rubber band do? Well, it goes flying through the air, but whenever you go and actually pick up the rubber band again, does it look the exact same shape that it did before? Yeah, because of this restoring force. And that's really what you're feeling whenever you're pulling it back. It's really wanting to go back to its equilibrium position where it was unstretched. So this can also happen in a spring. With a spring, though, you can take the spring and you can either pull it so you could stretch it, or you could even push it and compress it in. So whenever you do that, it's going to want to get back to that equilibrium position, whether it be outside of that, from being pulled, or, compressed. Okay, so let's look at some pictures. So this is a spring that would be, and this is like length, and the 0 is like the initial or the equilibrium length. So if you pull it out, then it's going to be greater than 0. But if you push or compress the spring, it's going to be less than 0, because it's going to be before that initial position. And you can see the force is, for this one anyway, is pulling back because it's wanting to go back to that original position. This one, however, is pushing against, so it's going the opposite direction. All right, and the change of the position, so S again is for the position here, the displacement from the equilibrium. And this equation is known as Hooke's law. So this is kind of the person that sort of figured this out, that you could figure out what the spring force is if you knew the spring constant, which is this K symbol inside the equation, multiplied by the change of distance. So it gives you this graph here, and actually, if we were in class, we could do a Hooke's law lab, and I'm going to have you do a Hooke's law lab simulation. But the spring force you could determine by putting it on the y-axis, putting the displacement on the x-axis, and you could actually find the slope, okay, of that, and that would be your K value. And the spring constant is basically just how rigid it is. So think about those really big rubber bands. They are going to have a lot more rigidity to them than like a really small rubber band would. So that spring constant is going to be a different number. So we're looking at this quick check 9.9. So this is showing the restoring force of 3 springs is measured as they're stretched. Which spring has the largest spring constant? So that would be, you got your force versus your displacement. So the largest spring constant would have the most slope. Okay, so the steepest slope, so that would be A. All right, so we've got another example here. Let's see, this is showing us that a figure, which it doesn't give us. Awesome, I get to draw something else. All right, so this is showing a mass of 2 kilograms attached to a spring. So let's kind of just draw a spring here. And it's attached to this toy train. Oh gosh, such pressure right now. I know, this is terrible. You know, it's really weird to write with this pen too, by the way. I know, I'm normally bad. And then draw a little thing here. See, it's a train. It totally looks like a train. All right. So this is showing that the mass is 2 kilograms and the train itself is going, 5 centimeters per second. And it's going this direction. All right. And it tells us that the spring constant is 50 newtons per meter. So if you go back a couple of slides, I don't know if it's going to let me or not. You go back a couple of slides here, you've got a force versus a distance, right? So if you're going to do the slope of that, it would be like your rise over run. So force is measured in newtons divided by your run, which is displacement, which is measured in meters. So that's where you're getting this Newton per meter unit. Okay, and then it goes on and it says that there is a static friction coefficient. So yay, we get to go back with that stuff, right? I know you guys are excited to hear. And it says that it's at equilibrium at t equals 0 when the train starts to move. And it wants to know when does the block start to slip. All right. So let's set up some stuff here. I didn't give myself very much room. All right. I'm going to draw a free body diagram really quick. So you've got a force that's going this way. You've got this spring force. And then you've got this static friction force that's kind of pulling, you know, that not really pulling, but opposing that mass to move. And then you've got a normal force and a gravitational force. Okay. So let's do our forces in the x direction. Okay. So we've got our spring force minus our static frictional force. Okay. And so spring force is going to be your negative. What is this wanting us to find, by the way? This is wanting us to find when. So it's actually wanting us to find time. Okay. So let's keep that in mind. And all right, so our spring force is going to be our spring constant times our displacement minus our frictional force, which I should have written out, is you've got that coefficient of static friction times normal. Okay, which I gotta write out again because, which I've run out of room. What is normal? How do you find normal? Mass times gravity. Okay, now we're trying to find, if we find the distance, we are given the velocity. Could we find time if we have those other two? Yes. So if we find this distance value right here, so delta S is our displacement. So we've got our coefficient times mass times gravity over K. Okay. And then we're going to plug in some numbers. So we've got 0.6 times the mass, gravity, over our 50 Newton per meter. So you should end up with a displacement of 0.235. Okay, now remember, velocity is equal to distance divided by time. So time is equal to distance divided by velocity. All right, so I'm going to take time is equal to distance divided by velocity. Oh no, I've got centimeters here. So I got to change that to 0.05 meters per second. Yeah, always make sure that your units are the same, and you end up with 4.7 seconds. Okay, so there's just an example of using spring force. All right, so I am going to talk about this maybe for a minute. I think my pen is actually about to go out on me, so I'm going to have to charge it for a minute, of course. So this stick slip motion, this is just saying that like earthquakes are an example of that. And you possibly remember hearing about tectonic plates in high school, and those tectonic plates are moving constantly. If they move enough, then they can cause quite a bit of damage. And so these large masses of rocks are somewhat elastic and can be stretched, but eventually if you go past that, so like if I take a spring even and I just like a slinky and I pull on that slinky, then I will basically cause it to deform. It's gonna exceed that force that it can withhold, and then my